give this presentation. At surgical operating theaters, 4 decades of CFD, I'm trying today to show the efforts spent to model air conditioning systems and energy systems in hospitals over the years. I work as a professor of energy at Cairo University and also Ashley Fellow. So of course you are aware that in hospitals we have many departments, and basically air conditioning in these spaces differ. And we all care about how the air comes into the space and how it leaves the space, depending on if it is an operating room or infectious or isolation or immunosuppressed rooms, as you've seen on the screen. Then we start by looking at the different categories of hospitals, from primary, emergency, and so on. I'll skip this. Of course, we have to look for the airborne contaminants and try to minimize this as per the ISO standards. Operating rooms. Typically in operating rooms we have cupola, which is the light fixtures, and we have the air coming from the ceiling. So how can we design air conditioning rooms? Of course we have guides from ASHRAE, and we have the ventilation healthcare facilities design guide, standards. We have also different standards for the clean room air standard. Pressure in the room is maintained. It has to be positive pressure in operating theaters, negative in infection rooms. Now, normally when you are operating in hot and humid countries and you get 100% fresh air, then the problem of excessive enthalpy is very important. And that's the proper specification of the outdoor conditions, temperature and humidity, affects the cooling capacity calculations. If you see here that the ventilation load, which is outside air load, takes a big chunk of the energy, almost 75%. That's to make the people comfortable, and we have to look into the factors affecting the thermal comfort of a human being. That takes activity, age, clothing, and so on. So to do this modeling, and I've been doing mathematical modeling for the past 40 years at least, we start by modeling the human being as a box, cube, and square. Now we can do this. We can model the proper hands, head, and everything. Perspiration, surface temperature, everything. Now, how can we do the design of healthcare facilities? Now, the poor guy, our patient, is to sleep on his bed. The dimensions of the bed are conventionally 0.5 meter by 2 meters. So why do we have this large space? If you look at the center of the room, you'll find the person sleeping with his hand like this. And now this is plot into the proper dimension. That's the area needed. First, we have to not only to put the person on the bed, but also to take into the equipment that are going to be used. Scan, thermography, and things like that. So we have to look into the air coming into the room, the positive pressure, the sound level, and also the pressure difference between the room and the other spaces, and these are related into the HTM in the UK. Yeah. Here are some examples of the rooms. Ideally, we'd like to have the air coming from the ceiling going into the floor. This will be a piston type air distribution, pushing, and there will be no pockets, there will be no possibility of any impurities or pollution in the room. But unfortunately, in operating theaters, we have to make anti-static flooring for the doctors when they are giving charges. This charge, electric charge, has to be going somewhere. And so we have in the floor anti-static electric network. So we cannot take the air from the underfloor. So we have to take them from the sides, and for that we have different designs. Of course, we have the lighting fixtures. This is one of the hospitals I designed. Nowadays, we have ready-made rooms where you have this like a capsule type. You have come and you integrate it on the spot. Of course, the problem of hygiene is very important, and we'd like to get rid of any pollutant possible by keeping the pressure relationship, air movement, and also the contamination. It's a balance between temperature control in the room and humidity. For isolation rooms, we have a special treatment where the pressure is kept negative, so the patient does not influence other people around him or get influenced himself. Of course, the light cupola or the light pendant itself used to be like sunshine before. Now, with the development of the lighting fixtures, became very, very low energy emitting surfaces. But still, that's how the operating room looks from inside. Now we go to the part where we model these spaces. And we use computer, the governing equations that we know, that I'm not going to talk about them today. So here, to the top is a vertical section in the room where we have the two members of the surgical team, and you have the cupola, and you have your air coming from the ceiling. This is your table, and this is another design. We can predict, so these predictions are at least 15 years old, of the velocities, temperature, relative humidity, and kinetic energy of turbulence. And this is for an empty room, no one inside. Then you start adding the human being, and you can see that the calculations are sensitive. And you can see near the human being, the relative humidity changes because of the perspiration of the person. Now we add also the lighting pendant, and you see also the distribution in the room changes. So we can get, with these calculations, the air distribution, temperature, and kinetic energy in the room, as well as the pollutants. Normally we use three-dimensional computer software, typically the grid size of about 8 million grid nodes on a PC. When I was doing my PhD at Imperial College, the maximum we could reach at that with my colleague Sraguddin used to be 8,000 points, 20 by 20 by 20. After that, the computer would say, sorry, bye-bye. Nowadays, on a laptop, you can reach 20 million grid nodes sometime. And this procedure is iterative, so it's complicated. But we still use a lot of turbulence models to be able to account for the different activities. So here are some examples of the immunosuppressed. Also, if you have transplant rooms, so you have two beds, this is a kind of the velocities and the temperature profiles. To me, a room, you have to put air from one side and you extract from one side, but you don't like any pollution to be remaining in the room. No residence time. So this young lady is trying to climb up the stairs to arrive at the indoor air quality, but there is one step in the middle missing, which is the air movement efficiency. We pay money to cool the air. Sure, I come from a very hot country. But we have to make sure that the air goes and makes every one of us comfortable before it leaves. And that's what we call a ventilation efficiency. Now, if we look at the operating rooms, we can divide it vertically into three stages, three zones. One of them is the dirty zone, which is the level below the operating table. Then we have the operating range, where the surgeon is working, and we have the supply range zone, where the air is coming. So we don't want any air to be coming from this zone, which is operating zone, to the supply zone. In another way, with this, we don't want any cross contamination from this zone. Down here is the dirty zone. Down here is the supply zone. So we calculate how we can maintain this. And we can do this by keeping the supply and extract locations to certain locations. Here, for example, you can see that the air coming from the ceiling acts like a curtain to preserve the operating bed zone in two systems, where you have a plenum, the first one on the top, and where you have individual grills, supply grills on the one on the bottom. So here at the end of the presentation, end of my paper, I'm trying to discuss the various possible arrangements. And you say, this is good, do it. This is bad, don't do it. And this chart explains these. I know I have to be in short of time. And I have also about 70 slides, so I'm not going to show all. But at the end, we have to be careful where we put the extract location and the supply, no cross-contamination between them. I'll give examples. Here is an operating room where you have the operating bed here, and you have your supply, and you have your extract from the corners of the room, surely to get an even distribution of the air out of the room. That's another hospital in Jordan. So the owner sent me this diagram. Can you air condition it? Of course, the architects who designed this room, the room is not, it has to be square, it has to be rectangle, but not like this. So anyway, we solved it, but we had to use computational techniques in order to see where we put the supply and what will be the result in terms of velocity distribution after certain times. That's another hospital, which is the traditional one. That's Suez Canal Hospital, where we have the supply coming from the ceiling and extracts at the corners, as indicated by these arrows, 1, 2, 3, and 4. So the recommendation is to use partitions around the central plenum in order to avoid any recirculation of the air. I'd like to thank my students, colleagues, and also my ISO technical committee collaboration. Thank you very much for your time. And at the end, this is the only one who appreciates my work. This is my cat, and he usually sits on my desk. This is his asylum. He runs away from my daughters. They are grown up now, but this is a place where nobody touches him. And this slide, I always put it, and people ask me, where is the hand? No, he has 2 hands. Thank you very much.